This is section 4.5, exponential and logarithmic equations. And we'll start off by solving exponential equations. Do make sure that you have your calculator with you. It's going to be really important that you can get the answers using the calculator. So if you have that, get it out. So the idea here, of course, is solving equations that have some sort of exponential component. And what you should see is in the first two examples, we have our variable in the exponent. So that's what makes it an exponential equation. You see that variable, it's up, it's up. So the A and B we're going to solve in two different ways. So each one I'll solve differently. But what I want to show you with A, we have 2 to the 4x equaling 16 to the 2x minus 1. So the idea here is there's a couple different ways we can do it. Because 2 has a relationship with 16, we can do this in a certain way. Because we can write 2 as a power, 2 to a power, that gives us 16. So what I mean by that is I have 2 to the 4x, and then on the other side here, I have 16 to the 2x minus 1. And I can rewrite 16 as 2 to the 2 times 2 times 2 times 2, 2 to the 4th. So I'm going to write 16 as 2 to the 4th. So that's just a rewrite there in parentheses. And then I'm going to have my 2x minus 1 here. Then we remember that we have 2 to a power and then raised to another power. And that when you have a power raised to another power, the operation that goes on between those two exponents is multiplication. So we can take the 4 and distribute to the 2x minus 1. So notice I have this. And then this is key. There is an exponential rule that says when you have two sides equaling something where you have the same base. So notice we have 2 to the 4x equaling 2 to the 8x minus 4. It's not surprising that what has to be true is, for this to make sense, we're trying to find the value of x that makes this true. To be able to find that, what has to be true is that our exponents have to be equal. So as you can see, we end up with 4x has to equal 8x minus 4. That has to be true. And now we can take this as a very straightforward linear equation now. So we've taken it down, we've been able to do something so that it's something that we recognize. And now we just solve it for x. You can pause if you want. Just a linear equation. And we end up with x equaling 1. And as you can see, so don't ever forget that, I'm going to put it in a solution set here. Don't ever forget that you're finding the value of x that makes this true. If we plug in 1, you'll notice that the left-hand side is 2 to the 4th. The right-hand side is 16 to the 2 minus 1. 2 to the 4th is 16. 2 minus 1 is 1, so that's 16 to the 1 or 16. So of course, we can always check our answer and say, yeah, that makes it true. No rounding needed here. I didn't even bust out my calculator on this. I was able to do it without it. But if you look at the part B here, question B, you see that we're solving 3 to the x equaling 10. And if you're thinking about, well, what exponent would I raise 3 to get 10? You should be thinking that that's going to be a challenge because 3 squared is 9 and 3 cubed is 27. But we don't have 3 to some positive integer that's going to give us 10. And so in this case, we can't do what we did in part A. But that's okay. So the idea behind a problem like this is we have that x in the exponent and we want to free the x. I'm trying to solve this for x. So at some point I need x equals. So somehow I have to free that x from being in that exponent. And the way to do that is to remember that when you have something like, for example, 3 to the x, The way that that x can come down is by using the power rule. So if you remember, the power rule allows us to bring the x or any exponent on a logarithm down. But I can't bring something in an exponent and a logarithm down until I have a logarithm. So what we can do, this is the idea here, is I can take the log of both sides. So that is a valid thing that you can do. You can take the log of both sides. I'm just going to write log, so you should recognize that what that means is that's base 10. If I just write log, that's the common logarithm, it's going to be base 10. But if you look at the left-hand side there, what it means is now I can take that x and I can bring it to the front and use it as multiplication. So x times log 3. Over on the side I have log 10, but understand, I can write this or not, but this is log base 10 of 10. And we have a property that says anytime you have a log with the same base and the same thing inside, your answer is, of course, just the exponent, because that piece there is saying 10 to what power gives me 10? Well, that's just 1. And then now we have, you want to understand that log 3 is just a number. Log 3 is just a number. So because of that, we can divide both sides by log 3 and get x equals 1 divided by log 3. And that is, like I said, just a number. That's the exact answer, because that is the exact answer there. However, if you were to put that in the calculator, so 1 divided by, and then log 3, you're going to get the decimal approximation. And notice it says round answers to 4 decimal places if needed. So I'll go ahead and round it to 2.0959. So do make sure you can get that answer. And I'll put that in a solution set. And of course, that is something you can check. So you could say, okay, 3 to the, put your exponent, 2.0959. I get 9.999964028. So that's going to keep going. So obviously that's not 10. And that's simply because my answer has been rounded. It doesn't mean it's not the correct answer. It's the correct answer to 4 decimal places. But if you had a situation where you weren't asked to round it, the true exact answer is 1 divided by log 3. So depending on what you're being asked for, maybe you round it, maybe you give the exact answer. You just have to pay attention to what you're being asked there. Okay, so if you want, I would suggest trying to do C. It is very similar to B. It has like another step or two, but it is very similar, so you're welcome to try it. I am going to actually do the same thing here. So I'm going to take the log of both sides. Even if you don't know the first step, if you want to pause it at some point and then just do the, just continue on whenever you get to the point where you think, oh yeah, I can do it from here. So we have 5 to the 2x minus 1, just trying to use a couple colors here. And then I have the 120 on this side. So I'm using log again. That's very common because if I need a decimal answer, I know that I can do log with my calculator, that common logarithm. So I'll do that. And then the same idea. I'm trying to free this exponent. So my logarithm allows me to free the exponent by using the power rule. So now I can bring that 2x minus 1 to the front. I'm going to keep it in parentheses though, because it is 2 terms. Then I'll have log 5, and that'll equal log 120. Now we need to solve for x. So the easiest thing, the most straightforward thing, would be divide both sides by log 5. So if I divide both sides by log 5, it's going to leave the left side. It's going to come to the right side and then be right here. Now, if you're looking at that like, whoa, that's just a number. Log 120 divided by log 5 is just a number. You can find it if you want. And then use, we're going to round eventually to 4 decimal places. So you could take it to 5 decimal places just to make sure that you can round correctly at the end to 4. Or you can leave it like that for right now. Then we want to solve for x. We just want the x by itself. So we need to bring that 1 over. We need to bring that 2 over. And in terms of order, we want to bring the 1 over first. And this really is just a linear equation at this point. It's just that it has this weird log 120 divided by log 5, but again, that's just a number. So we'll add 1, and then we're going to divide by 2. So our final answer is log 120 divided by log 5 plus 1, whew, that's a whole lot of something, divided by 2. Oh yes, okay. So you want to try to put that in your calculator. You can do it in steps. You can do it all at once, but you want to make sure that you can get it. And if you do it correctly, you should get 1.9873 to 4 decimal places. So, just pay attention to making sure that you can get that answer. That is important. Now, you'll notice, well, maybe you'll notice, 5 squared is 25. 5 cubed is 5 times 5 times 5, which is 125. So when we look at C, what we want to understand is the exponent that's going to be on that 5, for it to equal 120, is going to be somewhere between 2 and 3, but it should be pretty close to 3 since 5 cubed is 125. And what we notice is if we put in 1.9873, that's very close to 2, and 2 times 2 is 4, minus 1 is 3. So our answer does make sense. It does, we have an exponent that's going to be very, very close to 3, but not quite, which makes sense because we don't have 125, we have 120. So just thinking about the fact that that kind of works. That's all I'm saying there. Okay. And then we have D. Now you'll notice D is a little bit different because D has an E. And the only difference between something like C and something like D is the fact that you have, instead of a 5 as your base, you have an E. But this actually kind of makes it easier because instead of using log, which we've used a couple times already, we could instead use ln. We could use the natural log. And I'll show you why that's so helpful. When we use the natural log to free our exponent, when we use natural log, you want to remember our properties, which say, if I have the natural log, which is log base e, of e to the 3x plus 1, that simplifies to just, I can do this in 2 steps if you want, it's the power rule, 3x plus 1 times ln of e. However, ln of e is just 1 because it's log base e of e, which has an exponent of 1. E to what power gives us e? 1. So that means that all we have here on the left side is actually 3x plus 1. So as opposed to our other situation where we had to divide log 120 by log 5, by using ln, because we have e, it actually simplifies things a little bit. And now you have just a linear equation because ln of 14 is just a number, because, it's just a number. And so you can, if you want, the easiest thing really is just to solve this linear equation by moving over the 1 and moving over the 3. So go ahead and pause if you want to do that yourself. Okay, and here's our exact answer. And then we can put that into the calculator. Notice we'd be using ln, not log. And it looks like we should get something like 0.5464. So make sure that you can get that answer is what you're getting, 5464. I'll put that in my solution set, and that is done. Okay, so the last exponential equation looks very different than what we've been seeing. And there's a reason for that, and that's because it is actually quite different. So we're seeing, this kind of wide variety right now of these, for good or for bad, that's what we're seeing. So with this, I want you to notice the key things here. We have 3 terms. So you should think trinomial. Your head should say, I have a trinomial. I haven't seen that. I have not seen a trinomial. And what you should notice is two of the terms have an exponent. That is a variable. And you should notice that e to the 2x and e to the x are what you have. And more importantly, you should recognize that e to the x squared is e to the 2x. So what you should notice is that you have e to the x and you have e to the x squared. Because of that, I don't know if this will trigger something that you've seen already that we've done, because we have done it, but this is a case where we want to use substitution. Substitution. And what I mean by that is we want to rewrite this in a way that we'll know how to solve. So if I let u equal e to the x, I'm going to rewrite this as something that looks quadratic. And when it looks quadratic, I'll be able to solve it in a way that I know how, that I remember. And then I can come back and deal with the fact that I have e to the x's. So we have u equaling e to the x, so u squared equals e to the 2x. So if you can, you can pause this, see if you can rewrite this equation using, instead of e's, using u's, now that we've made this substitution. If you do that, you should see that you have u squared plus u minus 12 equals 0. Again, it's a very common math thing to take something that you've seen before and rewrite it into see something that you've never seen before and rewrite it into something you've seen before. So now we have this quadratic and we say, well, I've solved many a quadratic equation in my life. Maybe it factors. So if you want, you can pause, see if you can factor this really quickly. Hopefully you see that you'll have 4 and 3 as the numbers that you need, with a positive 4 and a minus 3. And then you should recognize that using our zero factor property, we get that either u equals 3 or u equals negative 4. Now, those are not our answers because we didn't start with u, we started with something that had x. So now we can do our back substitution where we switch the u back to e to the x, and we switch the u back to the e to the x because that's what we called u, and we have this. And now we basically take ourselves back to the last example, except it's even more simple because it's just e to the x equals 3. So the easiest way to simplify this is to now do ln of both sides. ln, so I'm just going to put them all here because I'm using blue, and then come back to my red so that it looks like this, just so you can see what I'm doing. E to the x and negative 4, and then we're fine. Okay, so notice that this will immediately simplify to just x, and that equals ln 3. The other side will also simplify to x, but we have ln negative 4. Now here's something to understand. Remember that what this is saying is over here. This is saying e to what power gives us negative 4. What we want to remember is that no matter what value I put in for the exponent, e to that thing is always going to be positive. You can think about it in multiple different ways, but if you think about the graph of e to the x, which is very similar as 2 to the x, 3 to the x, it doesn't have any negative y values. There's no value of x that you can put in that's going to give you something that is negative. So there is no solution to the ln of negative 4. And so this is just not a solution. That's all we have to understand. ln negative 4, I mean, you can try it, go ahead. If you put it on your calculator, you put in ln negative 4, boop, oh, domain error, there's a problem. And that's because, again, if you think about, you could even think about the graph of ln. ln's going to come up, those log functions come up and look like this. They don't have, you'll notice, any negative values of x. And so that's why you can't do ln negative 4. So it's not a solution. But ln 3 is fine. So that's our solution there, is ln 3. Okay, or since it wants a decimal, you can just go ahead and do ln 3 and see what you get. and I'm going to get 1.0986 as my 4 decimal approximation. Woo! Oh my gosh, one last thing here. All right, so let's do one last thing with our exponents here. This is compound interest. You may remember we have seen compound interest. It is that the amount that comes out is based on the principal times e to the RT, and that's because it's compounded continuously. So you can go back and find the formula if you want. But whereas before we were doing a plug and chug, now you'll find that that's not what we're being asked here. So remember, if you want, these are the things we have to think about. So if you want, take a moment, pause, and fill in which of those things do we have and which one are we trying to find. So that would be a great thing to pause and try to do. So this tells us that Sarah wants to have $50,000 for a down payment on a house. So she wants to end up with $50,000. So here's my $50,000 right here. She's going to invest $20,000. That's that P, the principal of what she's investing. And it's going to be continuous, which we know. And the rate is 4%. So we want to write that as a decimal. The question is, how long will it take? How long? How long? So that is not surprising that that is T. How long is T? So now we're going to plug in what we have, what we know, to solve for what we don't. So I'm going to move this over just a little bit. We have 50,000 equaling 20,000. E to the RT, so 0.04 T. So you may be looking at this and going, okay, I get it. This is not a plug and chug because we're trying to solve this for T. We're trying to get T by itself here. And so it looks kind of similar to some of the other stuff we've done where we need to free the T. We need to free the T. So in order to free the T, I'm going to start by isolating my E term here. So notice that's multiplication. So you might say, oh, I know we need natural logarithm. And I'll say, yes, we do need natural logarithm. But first, and before we can do that, we want to get the E by itself. So we want to just have our E to our exponent there. Now, dividing both sides by 20,000 gives us a number equaling E. And this is the point where we can free the T. So by taking the ln of both sides, which again is really the best idea if you're dealing with some sort of question about E, because it's that natural logarithm that occurs in the world. When we do this, we can free the T. So we remember that still ln 2.5, but on the other side, we can free the T. Because, as we've already talked about, this immediately goes to this. That is how it simplifies, because it says e to what power gives me e to the 0.04t. The answer is 0.04t. And then, now just our last step. We are just isolating the t, getting that t by itself. I'm going to just switch these so that I have t equals. And I don't know why I did that. So our answer, it looks like, will be ln 2.5. Here we are. ln 2.5 divided by 0.04. And we can put that into the calculator and see what we get. It's going to be pretty common because we wouldn't say, oh, how long will it take you to make your money? And then they go, oh, it'll take ln 2.5 divided by 0.04 years. Nobody says that. So we put that in the calculator and we get something like about 22.907. We are told to round to the nearest tenth. So we'll go ahead and say about 22.9 years. So almost 23 years to go from 20,000 to 50,000 at a rate of 4% compounded continuously. So that's a bunch of examples of exponential equations.